Picture for a moment the oldest darkness you can imagine, not the darkness of a power cut or a moonless country road. The darkness of a universe that has not yet decided what it wants to be. No stars, no galaxies, no light of any kind. Just hydrogen, vast, cooling, primordial clouds of the simplest atom in existence, drifting through a space that is still figuring out its own geometry, still stretching in every direction at once, still hot and violent and utterly, cosmically blind. This is where we are going. And then, like a match struck inside a cathedral the size of everything that has ever existed, something ignites. We found it in May 2025. It arrived in the form of a signal so faint that for weeks the astronomers studying it refused to trust what they were seeing. They ran the numbers again. They questioned the instrument calibration. They went back to the raw data, back to the spectroscopic readings, back to the infrared photons that had been travelling for 13.53 billion years before being collected by a mirror the width of a tennis court floating 1 million miles from Earth, a gravitational shadow of our moon. The signal held. The number confirmed itself with a precision that left no ambiguity, no escape, no comfortable alternative explanation. A galaxy, a fully assembled, chemically enriched, blazingly luminous galaxy, exists at a redshift of 14.44. Its light left home just 280 million years after the Big Bang. It is called MOMZ-14, and it is the most distant object any human instrument has ever confirmed. It is also, in a deep and troubling sense, completely impossible. Or rather, it forces us to confront the fact that our story of how the universe began making things, our entire cosmological narrative of how darkness became stars, and stars became galaxies, and galaxies became the architecture of everything we can see, may be wrong in ways we have not yet identified and cannot yet measure. But that is only the beginning, because MOMZ-14 did not arrive alone. It arrived alongside a cascade of discoveries, impossible galaxies, evolving dark energy, oxygen in places it has no business being, biosignatures on a world 124 light-years away, and a tension running through the deepest foundations of physics that refuses, after a decade of trying, to go away. The James Webb Space Telescope is not just showing us the universe more clearly, it is showing us that we have been wrong about it, and we are only beginning to understand how deeply, and in how many directions, that wrongness runs. 3 questions are going to follow us through everything that comes next. Where did MOMZ-14 come from, and how did it grow so large so fast? What does the growing body of Webb evidence tell us about the dark energy that governs everything? And why does it appear to be changing? And when we look at a distant planet glowing with the chemical signature of life, how do we know we are not seeing exactly what we think we are seeing? We do not have full answers to any of those questions, but the process of asking them, the extraordinary hard-won, decades-in-the-making instrument that is now finally letting us ask them properly, is one of the most consequential things our species has ever done. Let us start at the beginning. Not the beginning of the telescope, the beginning of everything. To understand why MOMZ-14 is such a shock to the system, you need to understand what the system was supposed to look like. You need the baseline, the elegant, mathematically precise, observationally verified model of cosmology that dominated the second half of the 20th century, and the first 2 decades of the 21st, the model that was so successful in explaining so much that an entire generation of physicists essentially stopped asking whether it was fundamentally correct and started treating it as settled ground. That model is called lambda CDM, or Lie CDM. To use the Greek letter that gives it its name is not a simple thing. It is not a diagram in a textbook or a sentence you can tweet. It is a dense mathematical framework describing the entire history and contents of the universe from fractions of a second after its birth until the present day, a framework that has been tested against every major astronomical observation of the last 50 years and has, with remarkable consistency, passed those tests. It is the reason why, when astronomers tell you that the universe is 13.8 billion years old, they say it with the same quiet confidence that a structural engineer expresses when she tells you a bridge will hold. The calculation is solid. The foundations have been checked. Lambda CDM rests on two pillars. The first is lambda lu, which is Einstein's cosmological constant, a number he originally inserted into his field equations of general relativity in 1917 in order to keep the universe from collapsing under its own gravity, then famously removed when Edwin Hubble showed that the universe was expanding and not static. Lambda came back in 1998 when two independent research teams studying the brightness of exploding stars called Type Ia supernovae made a discovery so unexpected that many physicists initially refused to believe it. Those stars, burning at a known luminosity and therefore usable as cosmic distance markers, were dimmer than expected, not by a little. By enough to indicate that not only was the universe expanding, it was accelerating in its expansion. Something was pushing space apart, pushing it faster and faster, overcoming the gravitational pull that should have been slowing everything down. That something received a name, dark energy, and its mathematical representation in Einstein's equations was lambda. The two men who led those teams, Saul Perlmutter and Brian Schmidt, shared the 2011 Nobel Prize in Physics with Adam Riess for the discovery. The second pillar is CDM, cold dark matter. This is the invisible scaffolding of the universe, the material that does not emit, absorb, or reflect any form of electromagnetic radiation, but which nevertheless makes up approximately 26.8% of the total energy budget of the universe compared to the ordinary matter made of atoms that you and I and every star and galaxy and planet are composed of, which accounts for a mere 4.9%. Cold dark matter is called cold because its particles move slowly relative to the speed of light, which matters for how it behaves during the early universe. Its existence was inferred from the rotation curves of galaxies. Stars at the outer edges of spiral galaxies like our Milky Way were moving far too fast to remain gravitationally bound to the galaxies if only the visible matter was providing the gravity. Something else was holding them in. Something we cannot see, something that casts no shadow, something that has been predicted for decades and has never been directly observed. Not once. And yet without lambda and CDM, the universe as we observe it today cannot be mathematically produced. The distribution of galaxies in large-scale cosmic structure, the temperature fluctuations in the cosmic microwave background radiation, the proportion of hydrogen and helium and lithium forged in the first few minutes after the Big Bang, all of it requires both dark matter and dark energy to come out right. The model is extraordinarily good at explaining what exists. It is also built upon two components, 95.1% of the total content of the universe, whose physical nature we do not understand and have never directly detected. This is, if you pause to sit with it, the single most extraordinary epistemological situation in the history of science. We have a model that works. We do not know what it is actually made of, but for several decades, this was treated as a problem for the next generation, a puzzle to be solved when better instruments arrived, better detectors, better colliders, better eyes on the sky. The model worked. Move on. Lee CDM also made very specific predictions about the early universe, about what cosmic dawn would look like when we finally had a telescope powerful enough to see it. Cosmic dawn is the period roughly 200 million to 1 billion years after the Big Bang, when the first stars and galaxies formed from those primordial clouds of hydrogen and helium. Lee CDM predicted, with mathematical precision, that this process would be slow. Galaxies take time to build. Dark matter collapses into halos first, then gas falls into those halos, then gas cools and fragments into stars, then those stars live and die and enrich their surroundings with heavier elements. Then more stars form, then more, slowly, generation by generation, until you have a recognizable galaxy. The whole process, in those early epochs, was expected to produce relatively few, relatively small, relatively faint structures. Cosmic dawn was supposed to look like a room with the lights barely on, a scattering of dim, uncertain, proto-galactic wisps. This is what the James Webb Space Telescope was built in part to observe, and this is where the trouble begins. Before JWST, the record holder for the most distant confirmed galaxy, was held by a series of Hubble observations, pushed over years of dedicated effort, and then extended by the combined power of Hubble and ground-based spectroscopy to a galaxy called GNZ11, sitting at a redshift of approximately 11, or 9, meaning its light left it when the universe was roughly 420 million years old. That record itself was remarkable, the product of decades of optical engineering and clever observational strategy. To go further required something new, something built specifically for this purpose. Something with a mirror 6.5 meters across, coated in gold to reflect infrared light, deployed in a sunshield the size of a tennis court, orbiting a gravitational sweet spot 1 million miles from Earth. The cost of building it was approximately $10 billion, spread across nearly 3 decades of development. The Hubble Space Telescope cost $7 billion by its launch in 1990, in dollars adjusted for inflation. JWST cost more than twice that. It was the most expensive science instrument ever built. It launched on Christmas Day 2021 from the Guiana Space Center in Kourou, French Guiana, atop an Ariane 5 rocket, and for 14 days, the engineering team at the Space Telescope Science Institute in Baltimore and the thousands of scientists who had given pieces of their careers to this machine did not breathe easily. There were 344 single-point failures in the deployment sequence, 344 individual mechanisms, hinges, latches, motor-driven actuators, any one of which, if it failed, could have ended the mission entirely. The mirror segments unfolded, the sunshield unfolded. Each of the 5 layers of the sunshield, each thinner than a human hair, separated correctly and tensioned into position. The secondary mirror extended on its tripod of deployable booms. The instrument's suite chilled to its operating temperature of 50 Kelvin, minus 223 degrees Celsius, cold enough that the infrared photons arriving from the most distant reaches of the observable universe would not be drowned out by the telescope's own thermal emission. It worked, completely and precisely as designed. On July 12, 2022, NASA released the first science images, and the world held its collective breath, while an instrument pointed at a patch of sky smaller than a grain of sand held at arm's length, and revealed thousands of galaxies, some of them from epochs that no human eye had ever accessed before. What JWST saw when it turned its gaze toward cosmic dawn changed everything, not in the way popular headlines suggested at the time, not in the Big Bang never happened, sense that spread like wildfire through social media before scientists could correct it, but in a more profound and lasting way, in the way that genuine discoveries always change things, by revealing that the map and the territory are not the same thing, by showing us that a model which describes the present universe with extraordinary accuracy contains errors in its earliest chapters that point toward missing physics, missing understanding, missing pieces of a puzzle far larger than we had appreciated. The question was never whether the Big Bang happened. The question was what happened next. And what happened next, JWST is beginning to show us, was stranger, faster, and more violent than almost any model predicted. At the centre of this revelation as of May 2025 sits a small blurry yellow smudge in an NRCam image, 240 light-years across in its physical extent, radiating ferociously, enriched with elements that should not yet exist, clearing a bubble of ionized hydrogen around itself in a universe that should still have been completely opaque, a galaxy called MOMZ14. We need to understand why it is impossible before we can understand what it is telling us. And to do that, we need to understand how a galaxy is supposed to be born. The universe at its birth was not a quiet place. The Big Bang produced a cosmos of extraordinary density and temperature, a state so energetic that for the first 380,000 years, matter and radiation were locked together in an opaque, glowing plasma, a fog so thick that light could not travel freely through it. Then, as the universe cooled to roughly 3000 Kelvin, electrons combined with protons for the first time to form neutral hydrogen atoms, and the plasma suddenly became transparent. The fog lifted, light that had been trapped and scattered for hundreds of thousands of years, flooded out in all directions. and we can still detect it today as the cosmic microwave background radiation, the oldest light in the universe, now cooled to a temperature of just 2.7 Kelvin, just 2.7 degrees above absolute zero, filling every corner of space with a faint, omnipresent glow that carries within its subtle temperature variations the imprint of every structure that would ever form in the universe. After recombination, as this moment is called, the universe entered what cosmologists call the cosmic dark ages. There was hydrogen, there was helium, there was dark matter, there was the faint heat of the CMB, and there was silence, no stars, no galaxies, no light at optical wavelengths. The darkness lasted for perhaps 100 to 200 million years, while dark matter slowly collapsed under its own gravity into sheets and filaments and halos, and hydrogen gas began to cool and condense, falling along those dark matter scaffolds toward the density peaks where gravity was strongest. The first stars began to ignite in those density peaks. They were nothing like the stars we know, without any elements heavier than lithium, without carbon, oxygen, iron, silicon, the elements that stellar nucleosynthesis over billions of years had not yet produced. They were enormous, some of them perhaps hundreds of times the mass of our Sun, burning at temperatures that dwarf any modern stellar interior, living their entire lives in a few million years before dying in catastrophic supernova explosions that seeded the surrounding gas with the first heavy elements, the first carbon, the first oxygen, the first nitrogen, the first iron. These primordial giants are called population 3 stars. They have been theorized for decades. They have never been directly observed. They are the grandparents of every star that has ever existed, including the one whose light currently falls on whatever surface you are sitting on as you listen to this. And then, from the rubble of those first stellar deaths, the first galaxies began to form, slowly, hierarchically, small structures merging into larger ones over hundreds of millions of years, assembling piece by piece like a cosmic jigsaw puzzle assembling itself in real time. That is the expected timeline. That is what the models said. But MOMZ 14 is blazing with the light of a billion stars, just 280 million years after the Big Bang. It contains roughly 100 million solar masses of stars. It is enriched with nitrogen at levels that imply multiple generations of stellar birth and death have already occurred within it. It is partly ionizing the hydrogen gas around itself, clearing a bubble in the primordial fog, and it is one of a growing and disturbingly numerous population of such objects, galaxies that appear, by every measurement we can bring to bear, to be far too massive, far too chemically mature, far too luminous for when they exist. They are called, with characteristic scientific understatement, the unexpectedly bright early galaxies. In less careful company, they have acquired a different name, the impossible galaxies. The first hint that something was seriously amiss arrived before JWST released a single official science image. In the weeks after the telescope achieved its operating temperature in early 2022, before the mirror alignment was even complete, astronomers with access to early engineering data began noticing objects in the background of calibration frames that looked, by their colours and brightness, like they might be extremely distant, extremely early galaxies. This was not supposed to happen. The calibration fields were not chosen for their scientific interest. They were chosen because they were available near enough to the ecliptic plane to be easily observed during commissioning. Nobody expected to find record-breaking galaxy candidates lurking in the background of a photograph taken to test an instrument's focus. But there they were by July 2022, before the first science program had formally run, a team led by Rohan Naidu, then a NASA Hubble Fellow and Pappalardo Fellow at the MIT Kavli Institute for Astrophysics and Space Research, a researcher who had grown up in Hyderabad, India, had dropped out of engineering school at 18, bought his first ever plane ticket, enrolled in the founding class of Yale US College in Singapore, discovered astronomy almost by accident while working with a professor who studied X-ray binaries, and then spent 5 years at Harvard rebuilding our understanding of the earliest stars by excavating them from within our own Milky Way. That team had identified a candidate galaxy at a photometric redshift, suggesting it existed in the first 400 million years of the universe. 6 other candidates of comparable or greater distance were identified by other teams in the same period. Naidu's team named their candidate Glass C13. At the time, the photometric redshift estimate placed it around Z13, making it potentially the most distant galaxy ever found, if confirmed. Several other groups found candidates at similar or higher redshifts. The astronomical community, accustomed to treating pre-publication photometric estimates with appropriate skepticism, applied that skepticism carefully and found that even when they applied it, the candidates did not go away. They were real, and there were far, far more of them than anyone had predicted. Let me give you the number that made cosmologists go quiet in rooms and start writing on whiteboards again. The number that set the LCDM community's collective coffee cup down with a slow, thoughtful thud. LCDM predicted that in the first 300 to 400 million years of cosmic history, extremely bright, massive galaxies would be extraordinarily rare. The theoretical models, produced by teams running some of the most computationally intensive simulations in the history of science, using supercomputers that consumed megawatts of electricity to simulate the evolution of hundreds of millions of cubic megaparsecs of cosmic volume. Those models predicted that the number density of bright galaxies in this epoch, galaxies shining at the ultraviolet luminosities Webb was detecting, should be vanishingly small. What Webb found was approximately 100 times more of them than predicted. Not 10% more, not twice as many, 100-fold excess. If you walked into a party expecting to find 2 people and found 200 instead, you would not assume you had miscounted. You would assume something was fundamentally different about the nature of the party from what you had been told. The reaction within cosmology was not panic. Science does not panic. But it was serious, measured, and characterized by a certain quality of focused urgency that indicates a field which has encountered a genuine problem and knows it. Papers began appearing within months of the first JWST data releases. They came from groups all over the world, from the United States, from Europe, from Australia, from Japan, from Chile, from Canada, and they all circled the same question from different directions. Why are these galaxies so bright? Why are there so many of them? And what does their existence tell us about our cosmological model? The first thing astronomers reached for was the simplest possible explanation: measurement error. In the earliest months of JWST operations, the instrument was not yet fully calibrated. The photometric redshifts, estimates of distance based on the colour of the light, could be off. A galaxy that appeared to be at redshift 12 might actually be a galaxy at redshift 3, with an unusual spectrum that mimicked the colour signature of a high redshift object. Instrumental artifacts could create the appearance of extremely bright, compact sources. Dust within early galaxies might be distributed differently than assumed, making galaxies appear less massive than they are. Each of these possibilities was investigated systematically, rigorously, and with the full weight of the global astronomical community's attention, and each of them, one by one, failed to resolve the excess. The calibration was refined. The photometric redshifts were confirmed spectroscopically for dozens of the best candidates, confirmed with NIRSpec, JWST's near-infrared spectrograph, which disperses the light from a galaxy into its component wavelengths, and allows astronomers to measure redshifts with an accuracy that cannot be manufactured by instrument error. Spectroscopic redshifts are not estimates. When you detect specific emission lines, the ultraviolet light emitted by hydrogen atoms at a known frequency, or the light from ionized oxygen at another known frequency, and those lines are shifted to longer wavelengths by a factor that corresponds to a redshift of 13 or 14, you know where this galaxy is in cosmic time. The measurement is as direct as it gets in astronomy. The spectroscopic confirmations came in over 2022, 2023, 2024, and 2025, and they confirmed what the photometry had suggested. These galaxies were real, they were extraordinarily distant, and therefore extraordinarily early, and they were brighter and more massive than the models said they had any right to be. A few of the most extreme candidates turned out to be different kinds of objects. The little red dots, which we will return to in considerable detail, but a significant population of genuinely overly luminous early galaxies remained, stubbornly, provocatively, irresolvably strange. Then came a second complication, which is, to my mind, one of the most philosophically striking aspects of this entire story. The excess is not just in the count of bright galaxies, it is in their chemical composition. Stars are made of hydrogen and helium in their earliest incarnation. As they burn, they fuse those elements into heavier ones: carbon, nitrogen, oxygen, silicon, iron. When stars die, particularly in the violent supernova explosions of massive stars, they scatter those heavy elements, those metals in astronomical parlance, into the surrounding gas, enriching it, seeding it with the building blocks of future stellar generations, and ultimately of planets and chemistry and biology. This process takes time. Multiple generations of stars must live and die before the interstellar medium of a galaxy becomes significantly enriched. In the standard cosmological model, the earliest galaxy should therefore be extremely metal-poor, made almost entirely of hydrogen and helium, with only trace contamination from the first supernovae. The degree to which a galaxy is metal-enriched is a clock. It tells you how many generations of stars have already lived and died within it. MZ14, at just 280 million years after the Big Bang, contains nitrogen, not trace nitrogen. Substantial nitrogen enrichment of the kind that the lead researcher Rohan Naidu described as similar to what you find in the oldest population 2 stars in our own Milky Way, stars that are themselves ancient fossils of the early universe, enriched by multiple generations of stellar death before the Sun even formed. And crucially, nitrogen is produced in the late stages of stellar evolution in ways that depend on specific stellar physics, and its abundance in MZ14 requires a population of extraordinarily massive stars, potentially supermassive stars, dozens or hundreds of times the mass of the most massive stars known in the modern universe, to have already lived out their brief incandescent lives within this galaxy. Stars with hundreds of solar masses burn through their hydrogen in perhaps 1 million years. The universe at the epoch of MZ14 is only 280 million years old. For this galaxy to contain the chemical enrichment it does, stellar generations must have been forming and dying at a rate, and at masses, that our current stellar physics does not predict in such a small, compact, early system. This is the enrichment paradox, and it is one of 3 paradoxes that MZ14 embodies simultaneously. The first is the assembly paradox. How did this galaxy grow to the mass of 100 million suns, the mass of the Small Magellanic Cloud, a satellite galaxy of our own Milky Way, in only 280 million years, when our models say the hierarchical assembly process needed far longer? The second is the enrichment paradox. How is this galaxy already chemically mature, containing nitrogen abundances that imply multiple generations of stellar death, when there has barely been time for a single generation of the most short-lived massive stars? The third is the ionization paradox. How is this galaxy already clearing a bubble of ionized hydrogen around itself, already beginning the process of reionization, the epoch when the universe's primordial hydrogen fog was burned away by ultraviolet light from the first luminous sources? When our models of reionization said this process should have been underway, but far from as concentrated and local as MZ14's immediate surroundings suggest. 3 paradoxes stacked on top of each other in one object at the edge of the observable universe. And that object is one of what appears to be a population of hundreds, possibly thousands, of comparable galaxies in the early universe, all sharing the same fundamental strangeness, all requiring some modification, potentially several simultaneous modifications, to our best theoretical understanding of how structure forms in the cosmos. I will admit, when I first read the paper by Naidu and his 45 co-authors describing MZ14, I had to put it down and simply sit with the implications, not because any single element of it is incomprehensible. Each individual anomaly has candidate explanations that are internally consistent. But the combination, the scale of the brightness excess, the chemical enrichment, the ionized bubble, all of it occurring at Z1444, just 280 million years after the birth of everything, forces you to confront the uncomfortable possibility that we are not dealing with edge cases or measurement noise. We are dealing with something the standard model genuinely cannot accommodate. Something that requires new physics or new astrophysics, or both, the question of which, and how much, and in what direction, is where cosmology finds itself today. But before we can understand the proposed solutions, we need to understand what else JWST has found that complicates the picture. Because MOMZ14, striking as it is not the only anomaly. It is not even the most philosophically troubling one. That distinction, and I use the word troubling deliberately, belongs to a set of observations that calls into question not just how fast galaxies form, but the nature of the energy that governs the large-scale fate of everything. There is a number at the heart of cosmology that everyone agrees on and nobody agrees about. It is called the Hubble constant, denoted h0, and it describes the rate at which the universe is currently expanding. The speed at which any 2 points in space, far enough apart to be unaffected by local gravitational interactions, are receding from each other. Edwin Hubble, working at the Mount Wilson Observatory in California in the 1920s, was the first to measure it from observations of galaxies and the redshifts of their spectral lines, establishing the observational foundation for what we now know as the expanding universe. For nearly a century, the Hubble constant has been the most important single number in cosmology. It sets the age of the universe. It governs the scale of cosmic structures. It is the keystone in the arch of the standard model. And for the past decade, two completely independent methods of measuring it have been returning different answers, not slightly different. Significantly, stubbornly, embarrassingly different. The first method looks backward, to the early universe. The cosmic microwave background radiation, that relic light from 380 zeros and years after the Big Bang, contains within its temperature fluctuations an extraordinarily precise record of the physics of the early cosmos. The Planck satellite, operated by the European Space Agency, mapped those temperature fluctuations to an angular resolution of a few arc minutes and derived a Hubble constant of approximately 67.4 kilometers per second per megaparsec. What this means practically is that for every megaparsec of distance between two objects, where 1 megaparsec equals 3.26 million light-years, those objects are receding from each other at 67.4 kilometers per second due to the expansion of space itself. The Planck measurement of this number carries an uncertainty of less than 1%. It is one of the most precise measurements in the history of cosmology. The second method looks forward to the local universe. It uses a carefully constructed ladder of distance measurements, starting from objects whose distances can be measured directly, parallax measurements of nearby stars, and working outward through Cepheid variable stars, whose pulsation period is directly related to their intrinsic luminosity, and which therefore serve as reliable standard candles, to the Type Ia supernovae that Perlmutter, Schmidt, and Rias used to discover cosmic acceleration in the late 1990s. This approach, refined over decades and currently spearheaded by the SHEs, Supernovae H0 for the equation of state, collaboration led by Adam Rias, returns a Hubble constant of approximately 73.0 kilometers per second per megaparsec. The difference between 67.4 and 73.0 might not sound like much. In cosmology, it is a gulf. The disagreement between these two measurements stands at approximately 5 to 7 standard deviations. A statistical impossibility if both measurements are correct and the model connecting them is accurate. A 5 sigma discrepancy is the threshold at which particle physicists declare a new discovery. It is the level of significance at which you no longer say, maybe it's noise. You say something real is happening here, and we do not understand what it is. This disagreement has a name. It is called the Hubble tension. and it has occupied the front lines of theoretical cosmology for the better part of a decade. Hundreds of papers have been written attempting to resolve it. Every conceivable source of systematic error has been hunted, identified, quantified, and, in most cases, found insufficient to close the gap. Alternative cosmological models have been proposed, tested, and in most cases found to solve the Hubble tension only at the cost of creating equally serious problems elsewhere. This is where James Webb enters the argument in a particularly decisive way. One of the first concerns raised about the Hubble tension was whether the local measurements, the Cepheid-based distance ladder, might be contaminated by measurement errors. Cepheid variable stars, at the distances required for the supernova calibration, sit in crowded galactic environments. They are not isolated points of light against a clean background. They are embedded in regions of active star formation, surrounded by other bright stars, embedded in dust, located in spiral arms where the stellar density is high enough to create confusion in the images. The worry was that some of the light attributed to individual Cepheids in Hubble Space Telescope observations was actually contamination from unresolved neighbouring stars, artificially brightening the apparent Cepheid luminosities and thereby distorting the distance estimates. JWST resolved this concern, not by eliminating the Hubble tension, but by eliminating the excuse with its 5-meter mirror and its infrared sensitivity. JWST can resolve individual stars in the same crowded galactic environments at 3 times the angular resolution of Hubble Space Telescope. In 2023 and 2024, JWST observed the Cepheid populations in the anchor galaxies used for the supernova calibration, including the Large Magellanic Cloud and the galaxy NGC 4258, and measured their brightness with an accuracy that was simply impossible for Hubble. The crowding problem turned out to be real, but small. When the contamination was properly accounted for, the local Hubble constant measurement barely moved. It shifted by less than a kilometre per second per megaparsec. The gap with the CMB-derived value remained essentially unchanged at 5 to 7 standard deviations. JWST did not solve the Hubble tension. It confirmed that the Hubble tension is real. This matters enormously because the Hubble tension, if it is real, implies that our standard cosmological model, the same model that struggles to explain MOMZ14 and the excess of bright early galaxies, is missing something. And what it is most plausibly missing, according to an increasing number of theoretical physicists, is something about dark energy. Recall that dark energy, in the standard Lie CDM model, is represented by lambda, Einstein's cosmological constant, a perfectly flat, perfectly uniform, perfectly unchanging energy density filling all of space at all times. This is the simplest possible form of dark energy, a constant. It was an extraordinary prediction when Perlmutter and Schmidt's teams first detected the acceleration of expansion, and lambda has described that acceleration with considerable accuracy for 25 years. But a constant is a very specific thing. If dark energy is not constant, if it changes over cosmic time, as some alternative models propose, then the predictions of the standard model for the expansion rate in the early universe, and therefore its predictions for the CMB-derived Hubble constant, would need to be revised. In the spring of 2025, the Dark Energy Spectroscopic Instrument, DESI, released its second major data release after surveying millions of galaxies across vast cosmic volumes. DESI is a spectrograph mounted on the Nicholas U. Mild telescope at the Kitt Peak National Observatory in Arizona, and it measures the 3-dimensional distribution of galaxies using their spectral redshifts, reconstructing the large-scale structure of the universe to a precision that dwarfs any previous survey. The pattern of galaxy clustering contains within it a geometric ruler, the baryon acoustic oscillations, or BOs, the imprint of sound waves that propagated through the early universe and were frozen into the large-scale structure at recombination, 380,000 years after the Big Bang. By measuring how those oscillations appear at different cosmic epochs, DESI can trace the expansion history of the universe with extraordinary precision. What DESI found was not what the standard model predicted. The data hinted, with a statistical significance that increased from the first data release to the second, that dark energy is not constant. It appeared to be evolving, changing in strength over cosmic history. A class of theoretical models called dynamical dark energy had long predicted such an evolution, and DESI's data began to look increasingly consistent with those models, and increasingly inconsistent with a simple cosmological constant. Then, in July 2026, a new analysis published in Physical Review D went further still, examining a specific and radical class of models called LSCDM, lambda sign switching cold dark matter, in which dark energy does not merely evolve smoothly, but actually changes sign over cosmic history. In these models, dark energy in the early universe was negative, not pushing space apart, but pulling it together, supplementing gravity rather than opposing it. Then, at some point in cosmic history, roughly when the universe was less than a third of its current age, the sign flipped. Dark energy became positive, began pushing space apart, and has been accelerating the expansion ever since. The reason this matters for MOMZ14 is profound. If dark energy was stronger, and especially if it was pulling things together rather than pushing them apart, in the early universe, then the rate at which structure formed in those first hundreds of millions of years would be different from what LSCDM predicts. Dark matter halos would collapse faster, gas would cool faster, stars would form faster, galaxies would assemble faster. The impossible brightness and mass of MOMZ14 and its companions in cosmic dawn might not be impossible at all. They might be precisely what a universe with a more complex dark energy history should produce. This is speculative. Let me be clear about that. The July 2026 analysis found that LSCDM reduces the Hubble tension, moves the predictions of the model in the right direction, but does not fully resolve it. The tension remains at reduced but still significant levels. The data is consistent with sign-switching dark energy, but does not conclusively require it. Alternative explanations, different early dark energy models, modifications to the neutrino sector, as yet unidentified systematic errors, remain on the table, but the convergence of multiple independent lines of evidence, the excess of bright early galaxies from JWST, the evolving dark energy from DESI, and the persistent Hubble tension from the entire global measurement program, these are not three separate problems. They may be three symptoms of the same disease, and there is a fourth symptom, one that arrived from a completely different direction, from the study not of the most distant galaxies in the universe, but of a small, warm, cloud-wrapped world in the constellation Leo, 124 light-years from Earth. The fourth symptom is the most personally resonant, because it is about life, or something that might be life, or something that generates one of the most important epistemological questions in the history of science, or possibly a chemistry experiment. We genuinely do not know, but we need to understand why not knowing has become, in the space of 2 years, one of the most consequential forms of uncertainty in all of science. 124 light-years from Earth, a planet 2, 6 times the radius of our own orbits, a quiet red dwarf star in the habitable zone. The region where liquid water can exist on a planetary surface or subsurface, and for the last 2 years it has been the most argued over piece of real estate in the solar neighbourhood. It is called K2-18b. It was discovered in 2015 by the K2 mission, the successor to NASA's Kepler Space Telescope, which detected its existence via the transit method, a fractional dimming of its host star's light each time the planet passed in front of it. K2-18b is not a rocky terrestrial world like Earth or Mars. It is a sub-Neptune, larger than Earth but smaller than Neptune, likely composed of a thick volatile envelope, water, methane, possibly supercritical water, surrounding a rocky or icy core. A 2023 paper published in the Astrophysical Journal Letters proposed that K2-18b might be a Haitian world, a class of potentially habitable planet, with a global liquid water ocean beneath a thick hydrogen-rich atmosphere, a class of world that Earth provides no analogue for, and that theoretical planetologists had been speculating about for less than a decade. Haitian worlds, if they exist, would represent a form of planetary habitability completely different from anything in our solar system. Their hydrogen-rich atmospheres would be deep and warm, maintaining liquid water conditions at pressures far above what a rocky terrestrial planet's surface would experience. Their oceans, if present, would be dark, warm, and potentially sheltered from the full UV radiation flux of the host star by the thick atmospheric column above them. They would be, theoretically, places where microbial life, not necessarily complex life, not necessarily anything like life on Earth, but life, could survive, metabolize, reproduce. Whether K2-18b is actually a Haitian world is not yet confirmed. Whether it has an ocean at all is not confirmed. It is exactly the kind of world that JWST, with its extraordinary ability to perform transmission spectroscopy, to analyse the light of the host star filtered through the planet's atmosphere as the planet transits, was built to interrogate. And when JWST interrogated K2-18b's atmosphere in 2023, it found carbon dioxide, it found methane, it found water vapour. These detections were remarkable in their own right. No telescope had previously achieved atmospheric detections of this quality for a sub-Neptune in the habitable zone. But they were not what generated the headlines that ran, in April 2025, through every major news organisation on Earth simultaneously. What generated those headlines was a signal in the data that appeared consistent with the presence of dimethyl sulfide. Dimethyl sulfide is a molecule with the chemical formula STREES. On Earth, it is produced almost exclusively by biological processes, specifically by marine phytoplankton and other microorganisms that generate it as a metabolic byproduct. It is the molecule primarily responsible for that specific brine-sharp smell that hits you when you step onto a beach near productive coastal waters. It wafts off the ocean's surface, enters the atmosphere in relatively small quantities, and has been proposed as a biosignature, a chemical marker whose presence in the atmosphere of an exoplanet could indicate biological activity. For decades of theoretical discussion, the key word in that discussion is almost exclusively biological. On Earth, the detection of a signal consistent with dimethyl sulfide in the atmosphere of K2-18b, announced in a paper published in April 2025 in the Astrophysical Journal Letters by a team led by researchers at the University of Cambridge, was accompanied by appropriate scientific caution, the same caution that characterized every statement by the scientists involved. Caution that speaks well of the field even as it was repeatedly overridden in popular media coverage. The signal, the team stated, was tentative. It was detected at a significance of approximately 3 sigma, strong enough to be worth taking seriously, not strong enough to constitute confirmation. The same caveat applies to dimethyl sulfide that applies to almost every potential biosignature. It could have an abiotic origin, a non-biological explanation we haven't thought of or haven't detected for a world with K2-18b's specific chemistry. The response from the scientific community was swift and rigorous in exactly the way good science demands. Within weeks of the April 2025 announcement, a NASA-led team published a reanalysis of the same JWST data using different atmospheric retrieval models and different assumptions about the baseline chemistry of a hydrogen-rich atmosphere. Their conclusion: the evidence for dimethyl sulfide was not conclusive. A separate analysis published in June 2025 found that the signal could be explained by combinations of abiotic chemistry, by reactions between methane, sulfur compounds, and other molecules that occur without any biological agency, in atmospheric conditions consistent with K2-18b's known properties. The debate has not been resolved. As of mid-2026, K2-18b sits in precisely the state that makes it both scientifically and philosophically extraordinary. A world about which we cannot say it harbours life, cannot say it does not, and from which the data we have is genuinely ambiguous between interpretations. But I want to dwell on the dimethyl sulfide question for a moment beyond its immediate evidentiary status, because it illuminates something important about how we think about life beyond Earth, and how difficult it is to do so without importing assumptions that are perfectly reasonable on Earth. and may be completely inapplicable elsewhere. On Earth, we have one data point for life, one example of the origin of life, one evolutionary tree, one set of metabolic pathways, one planetary chemistry. Every biosignature we have proposed, every chemical or atmospheric marker we have suggested might indicate life on another world, is derived from that single example: oxygen, methane, nitrous oxide, dimethyl sulfide. We identify these as biosignatures because on Earth they are produced in biologically meaningful quantities by biologically driven processes. But Earth is a rocky world with liquid water at its surface, a specific atmospheric pressure, a specific radiation environment, a specific geological history. K218b is none of those things. It is a sub-Neptune with a hydrogen-rich atmosphere and a potentially massive liquid water layer at enormous pressure, orbiting a dim red dwarf with a different ultraviolet flux profile than our Sun. The chemistry available to a microorganism, if one exists there, and the chemistry available to purely abiotic processes in such an atmosphere may differ from Earth in ways we have not yet modelled. This is the biosignature interpretation problem. Even if we detect a molecule that on Earth would indicate life, we cannot straightforwardly conclude that on K218b it indicates the same thing. It is a problem with no clean resolution. It is also, in its own way, one of the most productive problems in science, because it is forcing the field of astrobiology, a discipline barely 30 years old, to think far more carefully and far more creatively about what life requires, what life does, and what the chemical signatures of life might look like in planetary environments radically different from our own. And it is a problem that only exists because JWST exists. No previous telescope could have detected the atmospheric composition of K218b at this level of detail. No previous telescope could even in principle have identified a tentative dimethyl sulfide signal in the atmosphere of a sub-Neptune more than 100 light-years away. That this is now a live scientific debate, that we are now in the position of arguing about whether a specific biological metabolite exists in the atmosphere of an alien ocean world, is itself one of the most extraordinary developments in the history of astronomy. The JWST data on K218b illustrates a pattern that runs through everything the telescope has found. It has turned what were previously theoretical or philosophical questions into empirical ones, questions that can now be tested, that generate real data, that must be argued about with evidence rather than speculation. Whether or not K218b harbours life, the fact that we can now make measurements that seriously constrain the answer is a revolution. It is not the revolution we might have hoped for. A clean, unambiguous detection of alien biology would be simpler, but it is the revolution that was actually possible with the technology we have built, and it is enormously more than we had 3 years ago. The impossible galaxies are real. The Hubble tension is real. The K218b biosignature is uncertain but not dismissed. 3 open problems, 3 simultaneously running threads, all generated by the same instrument, all pointing toward the same fundamental conclusion. The universe is stranger than our best models, in ways that we are only beginning to see clearly enough to describe. And we need to understand who built the instrument that is making all of this visible. Not just the hardware, the mirror, the detectors, the sun shield, but the people, the decisions, the decades of struggle, of cost overruns and schedule slips and near cancellations, the human story inside the machine, because that story, it turns out, is as extraordinary as anything the telescope has found. The James Webb Space Telescope was supposed to launch in 2007. That sentence deserves a moment. The telescope that is now breaking records and rewriting cosmology every few months, the instrument that has become synonymous with the cutting edge of human astronomical achievement, was supposed to be in orbit and collecting data before the iPhone existed. The fact that it launched on Christmas Day 2021, 14 years behind schedule, and with a cost overrun that took the program from an initial estimate of $500 million to a final tally of just under $10 billion, is not just a story of technological complexity. It is a story of scientific commitment, of institutional stubbornness, of the particular human determination required to carry a single idea through 3 decades of setbacks, budget crises, political fights, engineering failures, and the quiet attrition of time. It begins in the mid-1990s. The Hubble Space Telescope, launched in 1990 with a catastrophically flawed primary mirror that was corrected by a famous servicing mission in December 1993, had become the most scientifically productive space science instrument in history. Its images of the deep universe, particularly the Hubble Deep Field, first released in January 1996, a 10-day exposure of a tiny previously blank patch of sky in Ursa Major that revealed approximately 3 the galaxies at various stages of cosmic history, had transformed public engagement with astronomy and established, beyond any reasonable doubt, that a space telescope capable of observing from ultraviolet through near-infrared wavelengths could reveal things about the universe that no ground-based telescope, however large, could match. But Hubble, operating primarily in visible light and near-infrared, could not see the most distant galaxies. The universe's expansion stretches the light from the earliest epochs into the infrared, wavelengths longer than visible red, invisible to human eyes, detectable only by cooled infrared detectors. Hubble's instruments pushed into the near-infrared, but the observatory itself was not cold enough to observe the mid-infrared without its own thermal emission overwhelming the signals from distant sources. To see the earliest galaxies, to observe cosmic dawn, you needed an observatory that operated in the infrared, was cold enough to suppress its own emission, and was large enough to collect sufficient light from sources that were faint to the point of near invisibility at these distances. In 1989, the Space Telescope Science Institute organised a workshop to discuss what should come after Hubble. The Hubble Successor Study, as it was initially called, identified the infrared universe as the frontier, the wavelength range where the next major leap in understanding awaited. Over the following years, as Hubble's science demonstrated how much could be learned from a space telescope, the scientific case for an infrared successor grew stronger and more specific. By 1996, NASA had committed to what was then called the Next Generation Space Telescope, or NGST, with a target launch date of 2007 and a cost estimate of $500 million. The original concept was austere, a relatively modest mirror, perhaps 4 meters in diameter, operating at liquid nitrogen temperatures, with a small instrument complement. The science requirements gradually inflated the design: a larger mirror for greater light collecting area, a more sophisticated cooling system, better instruments, a larger sun shield. By 2002, when NASA renamed the program the James Webb Space Telescope, in honour of the NASA administrator who had overseen the Apollo program, the cost estimate had already risen to $2 billion, and the launch date had slipped by years. The name choice itself was not without controversy. James E. Webb, who served as NASA administrator from 1961 to 1968, oversaw not only the Apollo program that would land humans on the moon, but also a Cold War-era federal bureaucracy in which LGBT employees were systematically investigated and dismissed, a practice known as the Lavender Scare that ran alongside the Red Scare and treated homosexuality as a security risk. A 2021 petition by LGBTQ+ astronomers and allies called on NASA to rename the telescope, citing archival evidence of Webb's involvement in or awareness of these purges. NASA conducted an investigation and concluded, in 2022, that no evidence had been found that Webb had personally directed these discriminatory policies, a conclusion that satisfied some and frustrated many others. The telescope retained its name. I mention this not to adjudicate the history. Reasonable people have disagreed about both the evidence and the appropriate response, but because it is part of the telescope's story, part of the human complexity layered into every great scientific institution, and to pretend it does not exist would be to tell a version of the story that is less true than the full one. Back to the engineering. By 2005, with the cost estimate approaching $4 billion and rising, the program was restructured. A new independent cost and schedule review found that the original plan was technically unrealistic and recommended a rebaselining, essentially a restart of the schedule and budget from a more honest foundation. The new baseline placed the launch in 2014 with a cost of $5.1 billion. It was the kind of moment that kills science programs. Large, expensive, over-budget space missions have been cancelled before for less. The James Webb Space Telescope survived because of the strength of its scientific case and because of the advocacy of the astronomical community, which recognised that nothing else on the horizon could do what JWST promised. But the restructuring did not stop the slippage. A combination of technical challenges, the 344 single-point failures mentioned earlier, are not abstract numbers. Each one represents an engineering problem that had to be solved, tested, verified and retested, and programmatic difficulties, including the effects of COVID-19 on the workforce at Northrop Grumman's facilities in Redondo Beach, California, where the telescope was being assembled and tested, pushed the launch date back again and again. 2018, 2019, 2020, 2021. Each delay was reported in the science press with a mixture of frustration and dark humour, the telescope having acquired an unfortunate reputation as the project that would never fly. Throughout all of this, the scientists and engineers who had committed years and in many cases careers to JWST continued working. Some of them had joined the program in their 30s and were approaching retirement by the time the launch finally occurred. Some of them had written their dissertations on JWST science cases that were predicated on the telescope launching in 2007, had spent a decade and a half updating those science cases as the technology evolved and the launch date receded, and were still working on those science cases when the first data finally arrived in 2022, 15 years after the original target. One of those people was Marcia Rieker. Marcia Rieker is a professor of astronomy at the University of Arizona, and she is the principal investigator for NIRCam, the near-infrared camera, the primary imaging instrument on JWST, the instrument that captured the image of MOM Z14, the instrument that produced the images of early galaxies that have rewritten our understanding of cosmic dawn, the instrument that has, in 3 years of operation, become one of the most scientifically productive pieces of hardware in the history of space astronomy. Rieck has been working in infrared astronomy for more than 40 years. She joined the University of Arizona in the 1970s, working initially on infrared detectors for ground-based observatories, and gradually built a career centered on using infrared light to study galaxy evolution, star formation, and the cosmic structures that are invisible at optical wavelengths. She was drawn to the JWST program in the late 1990s, when the instrument complement was first being designed by the recognition that NIRCam, if built with the required sensitivity, angular resolution, and wavelength coverage, could do something no previous instrument had done: directly image the first galaxies, the first star-forming structures, the first luminous objects in the universe. It would be, in astronomical terms, a form of time travel. Look far enough, with an instrument sensitive enough, and you see the universe as it was when it was young. Rieck's team spent over 2 decades designing, building, testing and refining NIRCam. The detector arrays at the heart of the instrument, sensitive to light between 0, 6 and 5 microns in wavelength, operating at 37 Kelvin to suppress thermal noise, read out by custom-designed application-specific integrated circuits that her team developed in collaboration with Teledyne imaging sensors, are engineering achievements in their own right, pushing the state-of-the-art in infrared detector technology further than any previous space astronomy mission had required. The testing process was, by multiple accounts from team members, a psychologically demanding experience. NIRCam was designed to work at temperatures and in an environment, deep space, 1 million miles from Earth, with no possibility of servicing. That could not be perfectly replicated in ground testing. There were moments when anomalies in test data required weeks of investigation before their source was identified. There were debates about whether specific design choices introduced risks that were acceptable or unacceptable. There were the ordinary human frustrations of a large engineering project: communications failures, contractual complications, the difficulty of coordinating a team spread across multiple institutions and time zones, overlaid on the existential anxiety of knowing that if NIRCam failed after launch, no one could go up and fix it. And then, on July 11, 2022, as NASA prepared to release the first official science images from JWST, Rick and her team sat at their monitors and watched the first NIRCam data from the galaxy cluster SMACS 0723 come in. The image showed thousands of galaxies. At the edges of the frame, invisible to any previous telescope, were faint smudges of light that had been travelling through space for billions of years to reach the telescope's mirrors. The level of detail, the gravitationally lensed arcs of background galaxies, the resolved structures within galaxies at cosmological distances, the sheer depth of the exposure achieved in 12 hours of telescope time was, in the words of several astronomers who saw it for the first time, almost too much to process emotionally. Rick has described that moment in interviews with characteristic restraint. She spent most of the night checking calibration data. She wanted to make sure the instrument was performing correctly. She trusted the image when the calibration confirmed what the data showed. This, I think, is the quality that characterizes the kind of scientist who builds instruments for 3 decades and does not give up. The ability to hold excitement and rigour simultaneously, to feel the wonder while simultaneously demanding that the wonder be verified, to be moved by the universe while insisting that your measurement of it be defensible against every possible criticism. It is not an easy balance to maintain across a career. It requires a certain kind of personality, one that is deeply in love with discovery, but deeply uncomfortable with claiming discovery prematurely. Rick was not alone in this. The entire JWST science team, hundreds of people across the world, shares this quality in varying degrees. But she represents something specific about the NIRCam story, about the imaging data that has produced the most publicly resonant of JWST's discoveries, and about the particular patience required to wait decades for an instrument to fly before you can find out if it does what you designed it to do. It did, spectacularly. But the human story of JWST is not only the story of the instrument builders, it is also the story of the scientists who have spent their careers building the theoretical framework against which JWST's observations are being tested, and who now find themselves in the extraordinary, disquieting, and ultimately exciting position of watching that framework strain under the weight of what the telescope is finding. Consider Sandra Faber, the Santa Cruz cosmologist who spent decades arguing for the importance of large-scale dark matter structure in galaxy formation, whose work helped establish the cold dark matter paradigm that forms the CDM half of low CDM, or Joel Primack, her frequent collaborator, who helped develop the first detailed simulations of structure formation in a cold dark matter universe in the 1980s, or Charles Conroy at Harvard, who supervised Rohan Naidu's doctoral work and who has himself been at the forefront of understanding the stellar populations that Webb is now revealing in these earliest galaxies. These are the people who built the map, and they are now watching, with a mixture of discomfort and genuine scientific delight, as the territory reveals itself to be different from the map, in ways that are both troubling and thrilling. There is a particular quality to the scientific experience of discovering that you were wrong about something important. It is not, in my view, as unpleasant as outsiders sometimes assume. Real scientists, the good ones, the ones who got into this, because they wanted to understand something real, tend, after the initial discomfort of confronting an anomaly, to find the wrongness exciting. It means there is more to discover. It means the universe is more interesting than you thought. It means you get to do more science, Rohan Naidu. In describing the discovery of MOM-Z14 in the press release announcing it, used a phrase that has stayed with me. It looks nothing like what we predicted, which is both challenging and exciting. That balance, challenging and exciting, is the emotional core of the current moment in cosmology. Not one or the other. both simultaneously because they are inseparable. The challenge is what makes the excitement real. You cannot be genuinely excited by a universe that simply confirms what you already thought. Naidu's own story adds another layer to this. He grew up in Hyderabad, India, far from the institutional centres of Western astronomy, and arrived in astronomy through a route that was, by his own account, accidental and non-linear. He dropped out of engineering school at 18. He enrolled in a liberal arts college he had never heard of before applying. He discovered astronomy working with a professor as an undergraduate in Singapore. He went to Harvard for his PhD, studied the chemical archaeology of ancient stars in the Milky Way, learned to read the stellar fossil record the way a geologist reads rock strata, and arrived at JWST with a set of skills perfectly suited to reading the chemical signatures of the most ancient galaxies in the universe. The skill set that Naidu brought to MOMZ-14, the ability to read nitrogen abundances in old stellar populations as markers of chemical evolution, came directly from his doctoral work on Milky Way archaeology, work that had no obvious connection to the study of the most distant galaxies in the universe. It was a conceptual leap, the fossils in our own galactic backyard, stars born in the ancient universe that now orbit within our Milky Way, preserving the chemical signature of that ancient epoch in their atmospheres. Those fossils can be compared directly with the light from galaxies like MOMZ-14, which allows us to cross-check what the ancient universe was doing. The Milky Way is, in this sense, a time machine that we can walk through on foot, and the most distant galaxies JWST observes are a time machine we can only see across 13 billion light-years of space. The fact that both machines are telling the same story, unusual nitrogen enrichment, signatures of supermassive early stars, is either a powerful confirmation or the most cosmic of coincidences. I lean toward the former. You will make your own assessment. There is, woven through the story of JWST, a thread of near misses and close calls that deserves acknowledgement, because it speaks to how differently things might have gone. The telescope was nearly cancelled in 2011, when the House Commerce, Justice and Science Appropriations Subcommittee moved to zero out JWST's funding entirely in the annual spending bill, citing cost overruns and schedule delays. The astronomical community mobilised with unusual speed and unusual force. Position papers, congressional testimony, letters from Nobel laureates, public statements from scientific societies, and the cancellation attempt was reversed in the final appropriations bill. Had it succeeded, the discovery of MOMZ-14 would not have happened. The Hubble tension would still be unresolved, because the crucial JWST confirmation of the Cepheid distances would not exist. The K218b atmospheric spectrum would have been measured by a smaller, less capable instrument, and the tentative dimethyl sulfide signal might never have reached detectable significance. The history of science is full of these contingencies, discoveries that almost did not happen, instruments that almost were not built, breakthroughs separated from non-existence by a single congressional vote, or a single funding decision, or a single engineer who stayed late to fix a problem that almost did not get noticed. We tend to remember the discoveries and forget the contingencies. But the contingencies are part of the story too, because they remind us that the knowledge we have is not inevitable. It had to be chosen, fought for, funded, built, launched and operated. And at each of those steps, there was a possibility of failure that did not occur only because enough people cared enough to prevent it. The $10 billion spent on JWST is sometimes cited as evidence of misplaced priorities, of a government spending cosmic sums on looking at the sky while more pressing earthly problems go unaddressed. I understand the argument. I do not entirely accept it. The history of fundamental science is full of examples where knowledge acquired for its own sake turned out to have consequences no one anticipated, but I understand it. What I would say in response is this: every discovery JWST has made belongs to every human being on Earth. MOMZ-14 is not the property of NASA, or the United States, or any institution. The light that left that galaxy 53 billion years ago, before the Earth existed, before the Sun existed, before all but the most ancient stars in our galaxy existed. That light belongs to whoever is curious enough to wonder where it came from, and the instrument that caught it, that held it steady in its golden mirror, and dispersed it into its component wavelengths and confirmed, to a fraction of a sigma, how old it was. That instrument is what happens when a civilization decides that looking farther than we have ever looked before is worth the cost. I find that worth sitting with. Let us go back to MOM Z14 itself, because we have not yet fully reckoned with it. The name is an acronym. MOM refers to the survey that found it, the Monsters of the Machine Survey, a JWST program specifically designed to hunt for the brightest, most extreme early galaxies in the cosmos field, a heavily observed patch of sky in the constellation Sextans that has been studied by nearly every major telescope of the last 2 decades. The Z14 refers to its approximate redshift, which spectroscopic follow-up confirmed at precisely 14.44. Rohan Naidu and his 45 co-discoverers published their findings in the Open Journal of Astrophysics in May 2025, with a paper titled with characteristic scientific ambition, A Cosmic Miracle, a remarkably luminous galaxy at Z-spec 1444 confirmed with JWST. Cosmic miracle is not hyperbole in this context. It is a quantitative statement. The number of galaxies as bright as MOM Z14 that LAU-CDM predicts should exist at redshift 14. 44 is vanishingly small. The probability of detecting even one in the survey area, covered by the Monsters of the Machine program, if the standard model is correct, is extremely low. The fact that one was found suggests either extraordinary statistical luck or, far more probably, that the standard model's predictions for this epoch are wrong by a factor large enough to make the rare not so rare after all. The galaxy itself is tiny by modern standards, 240 light-years across. For comparison, the Milky Way is approximately 100,000 light-years in diameter. MOM Z14 is a compact, dense, ferociously productive proto-galaxy, a system in the grip of a star formation event so intense that it outshines everything its small size would suggest it should be capable of. This is one of the hallmarks of the bright early galaxy population. They are not large galaxies in the way we understand large galaxies. They are concentrated, turbulent, blazing with the light of stars forming at rates that would be considered extraordinary even in the most active modern starburst galaxies. The mass estimate, approximately 10 to the power of 8 solar masses, comparable to the Small Magellanic Cloud, is crucial. In LAU-CDM, building a system of this mass through the hierarchical assembly of smaller structures in only 280 million years requires the dark matter halo formation process to have proceeded at the absolute maximum efficiency allowed by the model, and requires the subsequent conversion of gas into stars to have occurred at an efficiency that exceeds what the standard stellar physics allows. Not by a little, stars do not form from gas with 100% efficiency. Most gas in a galaxy never makes it into stars. It is blown out by stellar winds, supernova explosions, the radiation pressure of massive young stars, the mechanical energy of accreting black holes. The standard models of stellar feedback, which describe all of these processes, predict that star formation efficiency in early galaxies should be somewhere between 10 and 30%. To produce MOM Z14's stellar mass in its available time, you need efficiencies that push toward the upper limits of even the most optimistic scenarios. Unless something about those efficiencies is different in the early universe. This is where the theoretical debate becomes most active and most creative. Several independent lines of theoretical work have converged on the possibility that star formation in the very early universe, in the first few 100 million years, when the universe was denser and the gas temperatures were higher due to the higher CMB temperature, when the density contrast between dark matter halos and the surrounding intergalactic medium was different from today, was genuinely more efficient, not because the physics was different, but because the initial conditions were. Denser gas collapses faster. More gas available per unit volume means more material to build stars from. Less interstellar dust in the earliest galaxies means less attenuation of ultraviolet radiation, and possibly different conditions for molecular cloud fragmentation. One theoretical proposal, which has gained increasing traction since the JWST bright galaxy excess became statistically undeniable, is that the initial mass function, the distribution of stellar masses produced when a cloud of gas collapses into a stellar nursery, was top-heavy in the early universe. A top-heavy initial mass function means that a higher proportion of the stars formed in those early epochs were massive, short-lived, and extremely luminous. This would do two things simultaneously. It would make early galaxies significantly brighter than our modern mass-to-light ratio, calibrations would suggest, making them appear more massive than they actually are from their luminosity alone. And it would accelerate the chemical enrichment of those galaxies, because massive stars live fast, die young, and scatter more heavy elements per unit mass than the lower mass stars that dominate the current stellar population. A top-heavy initial mass function would, in other words, solve both the brightness excess and the enrichment paradox in one move. The problem is that we have no direct observational evidence for a top-heavy initial mass function in the early universe. It is inferred from the anomalies it would explain, rather than measured directly. This is not unusual in science. Many important parameters are inferred from their consequences before they are measured directly. But it means the explanation remains in the category of well-motivated hypothesis, rather than confirmed mechanism. Then there is the supermassive star hypothesis, the unusual nitrogen enrichment in MOMZ14, the same enrichment pattern that Naidu recognizes from old stellar fossils in the Milky Way, requires, in at least one well-developed theoretical scenario, the existence of stars with masses perhaps 1,000 to 10,000 times the mass of the Sun. These theoretical behemoths, sometimes called quasi-stars or black hole stars in different models, would be fundamentally different from any stellar object known in the modern universe. They would not be supported by the radiation pressure of nuclear burning in the usual sense. Some models suggest they would be powered in part by the accretion of surrounding gas onto a central black hole, with the black hole's accretion luminosity contributing to the energy budget of the stellar object. They would be almost unimaginably bright, single objects potentially outshining entire modern galaxies, and almost unimaginably short-lived, burning through their mass in perhaps 100,000 years or less. The existence of such objects, sometimes called population 3 stars in their most extreme theoretical incarnations, though the terminology is used in overlapping ways by different communities, has been predicted in theoretical models for decades. They have never been observed. The challenge is that any individual star, even one of extraordinary mass, is far too faint to be detected individually at the distances of MOMZ14. What we see is the integrated light of the galaxy, and within that integrated light are the chemical signatures that imply what the individual stellar objects must have been like. The nitrogen enrichment in MOMZ14 is, in this reading, a fossil record, not of individual stars preserved in time, but of the chemical output of a stellar population that lived and died before the universe was 300 million years old. The parallel to Naidu's doctoral work could not be more direct. His dissertation, completed at Harvard under Charles Conroy, was literally about reading the chemical fossil record of ancient stellar populations in the Milky Way. He spent 5 years developing the techniques, the spectral analysis methods, the understanding of how chemical abundances translate into stellar evolutionary histories. Then he joined JWST as one of its first scientific users, and the first galaxy he confirmed at a record-breaking redshift turned out to contain exactly the chemical signatures his doctoral training had equipped him to read. There is no pre-planned narrative here. Science does not work that way. But the alignment between a researcher's particular expertise and the specific anomaly revealed by the most powerful telescope ever built is, at minimum, satisfying. Science sometimes has the quality of a detective story, where the person who solves the case turns out to have exactly the skills required. The difference between science and a detective story is that in science, the case never fully closes. The ionization bubble around MOMZ14 adds another dimension to the strangeness, the epoch of reionization, the period when the first luminous sources in the universe burned away the primordial hydrogen fog and made the universe transparent to ultraviolet light. The period that JWST was specifically designed to illuminate was expected, in the standard model, to be largely complete by about 500 to 600 million years after the Big Bang. The bubble around MOMZ14 indicates that at just 280 million years after the Big Bang, at least some local regions around the brightest early sources were already being ionized. This is earlier than the reionization models predicted, and it implies that the photon output of the first generation of luminous sources, the ionizing ultraviolet radiation from massive young stars and possibly from accreting black holes, was significantly higher than the standard models assumed. A 2024 study from McDonnell Observatory, using JWST data from a range of early galaxy observations, found that reionization may have effectively ended at least 350 million years earlier than the standard model predicted. This is a shift of cosmic significance. If reionization was complete by roughly 700 million years after the Big Bang, rather than the standard model's 1 billion years, then the first generation of luminous sources was producing ultraviolet photons at rates roughly 3 times higher than previously calculated. This is consistent with the bright galaxy excess. More photons because more massive, more efficient, more luminous stars. And with the possibility of a top-heavy initial mass function driving higher stellar luminosities per unit mass, all of these threads are pulling in the same direction. The early universe was brighter, faster, more violent, and more chemically productive than LCDM predicted. The question of why is not yet answered. The range of possible answers, modified stellar physics, modified dark energy, modified dark matter models, new families of exotic particles, or simply a more careful accounting of mechanisms that exist within LCDM, but whose effects have been underestimated, remains genuinely open. But the question is now sharply defined, which is progress of a specific and valuable kind. A question you can state precisely is a question you can eventually test. The stakes of getting the answer right are difficult to overstate. Our understanding of how galaxies form is not merely an academic interest. It is the foundation of our understanding of how planets form, because planets form from the heavy elements that stellar nucleosynthesis produces and supernovae scatter. It is the foundation of our understanding of how life emerges, because life requires those heavy elements, carbon, oxygen, nitrogen, phosphorus, sulfur, to exist in the right concentrations in the right environments. If the early universe was producing heavy elements faster, at higher efficiencies, in more compact and intense environments than we thought, then the timeline for the emergence of the raw material of life in the universe is different from what we calculated. The first places in the universe where the chemistry of life was possible may have appeared earlier, hundreds of millions of years earlier, than our models suggest. This is the kind of implication that sends ripples across disciplines. Astronomers, planetary scientists, astrobiologists, chemists, physicists, all of them are affected by the question of when and how the first heavy elements were produced and distributed, and all of them are now waiting with the focused, careful attention of people who know that the next few years of JWST data may contain the answer. But there is a fifth thread running through this story, one that is, in its own way, more destabilizing than any individual anomaly, because it does not point to a specific missing mechanism or a specific wrong assumption. It points to the possibility that we are missing something at the deepest level, not just in the details but in the foundations. This is the question of dark energy, not whether it exists. The evidence for cosmic acceleration is overwhelming and multiply confirmed, but what it is, and whether it is really constant, and what the consequences of its evolution might be for everything from early galaxy formation to the ultimate fate of the universe. Let us take stock of where we stand with dark energy, because the picture has changed significantly in the 2 years between 2024 and 2026. and the change is not yet widely understood outside specialist circles. For 25 years, since the Nobel-winning discovery of cosmic acceleration, dark energy has been treated in essentially all standard cosmological calculations as a constant. Lambda, fixed, immutable, filling space at a constant energy density that acts like a repulsive force pushing space apart at an accelerating rate. This was not because anyone had strong theoretical reasons to believe dark energy was constant. It was because the data was not good enough to distinguish a constant from a slowly evolving quantity. Lambda was the simplest model that fit the data. Simple models are preferred when they work. Lambda worked. The DESI instrument changed the data quality. DSI is, by most measures, the most powerful cosmological survey instrument operating today. Its 5,000 fibre optic spectrographs, mounted on the focal plane of the Nicholas U. Mile 4-metre telescope at Kitt Peak, can simultaneously measure the redshifts of 5,000 galaxies, allowing it to map the large-scale structure of the universe with a speed and precision that is an order of magnitude beyond any previous survey. Over its first two data releases, in 2024 and 2025, DESI measured the positions and redshifts of tens of millions of galaxies spanning a huge range of cosmic epochs, reconstructing the three-dimensional distribution of matter with a precision that allowed it to measure the baryon acoustic oscillation signal to sub-percent accuracy. That BAO signal is the cosmological clock we mentioned earlier, the frozen imprint of sound waves from the early universe, preserved in the clustering pattern of galaxies, measurable across different cosmic epochs to trace how the expansion rate of the universe has changed over time. If dark energy is constant, the BAO signal evolves in a specific, predictable way with redshift. If dark energy is evolving, the BAO signal deviates from that prediction in ways that depend on how dark energy is changing. What DESI found is that the BAO signal is not consistent with a cosmological constant at a statistically significant level. The data prefers models in which the dark energy equation of state, the ratio of pressure to energy density, denoted W in the standard notation, is not equal to -1, as a cosmological constant requires, but instead varies with time. The statistical significance of this finding increased from the first DESI data release to the second, reaching levels that, in the standard particle physics convention of reporting results, would be considered approaching evidence, 3 sigma, but not yet reaching discovery, 5 sigma, for departure from lambda. Importantly, DESI's findings are consistent with the direction that the Hubble tension itself points. The Hubble tension exists in the standard framework because the early universe prediction of H0 from the CMB and the late universe measurement from the Cepheid supernova ladder disagree. If dark energy is evolving, if it was different in the past than it is today, then the prediction of the current expansion rate derived from early universe physics would need to be revised, potentially in the direction of agreement with the local measurements. The Hubble tension might, in this framework, be a symptom of our incorrect assumption that dark energy is constant. The July 2026 analysis of sign-switching dark energy, the LCDM models, represents the most radical version of this hypothesis. In these models, dark energy was not merely different in the past, it was negative. A negative cosmological constant pulls space together rather than pushing it apart. A universe with a negative cosmological constant in its early history would have compressed structure formation into a shorter time frame, creating conditions more favourable for the rapid assembly of massive early galaxies. It would have enhanced the rate at which dark matter halos collapsed and gas fell into those halos. It would have accelerated the whole process of cosmic structure formation in exactly the way that the JWST bright galaxy excess demands. This is, to my mind, one of the most consequential theoretical developments in cosmology in the last decade. Not because sign-switching dark energy is confirmed, it is not. Not because LSCDM is the correct model, we do not know. But because the convergence of multiple independent anomalies, the JWST galaxy excess, the DESI Bow deviation, the Hubble tension, all pointing simultaneously toward modifications in the dark energy sector, is not the signature of noise. It is the signature of a genuine physical effect that we are not yet measuring correctly. Let me illustrate what is at stake with a specific number. The cosmological constant, lambda, has a measured value of approximately 1.1 times 10 amnesa squared per square metre in SI units. This extraordinarily small number is itself deeply mysterious, because quantum field theory, our best description of the particle physics of space itself, predicts that the vacuum energy of quantum fields should contribute to lambda with a value approximately 120 orders of magnitude larger than what is observed. The discrepancy between the measured cosmological constant and the theoretically expected vacuum energy is the largest discrepancy between theory and observation in all of physics. It is called the cosmological constant problem, and it has been recognized as one of the most fundamental unsolved problems in theoretical physics for 4 decades. The reason lambda is so small, 120 orders of magnitude smaller than the naive quantum field theory prediction, is unknown. There is no mechanism in the standard model of particle physics that explains why the vacuum energy should cancel so precisely, leaving only the tiny residual that drives the current cosmic acceleration. Some theorists have argued for anthropic explanations. The universe has the value of lambda it does, because a larger value would have prevented galaxies from forming, and we would not be here to observe it otherwise. Others have argued for a landscape of possible vacuum energies, with our universe occupying a specific bubble in the multiverse, with the right value for structure formation. Neither explanation is testable in the conventional scientific sense. If dark energy is not lambda, not a constant, but a field or a more complex entity that evolves, then the cosmological constant problem does not go away, but it becomes a different problem. Instead of needing to explain why the vacuum energy cancels to 120 decimal places, you need to explain the dynamics of a field whose equation of state varies over cosmic time in a specific way consistent with Desi's measurements. This is still profoundly difficult, but it is a different difficulty, one that connects to active areas of theoretical physics, scalar field theories, quintessence models, modified gravity theories, that have viable physical frameworks even if they remain untested. The Desi data, combined with JWST's bright galaxy excess and the Hubble tension, is effectively saying to theorists, here is your constraint. Whatever dark energy is, it cannot be a simple cosmological constant and be consistent with all the observations simultaneously. You need to find a model that accommodates an evolving dark energy, explains the accelerated structure formation in the early universe implied by MOM Z14 and its companions, and resolves the Hubble tension. Those 3 requirements taken together constitute the most specific and demanding set of constraints that observational cosmology has ever placed on theoretical physics. No model currently in the literature satisfies all 3 simultaneously. This is not cause for despair, it is cause for work. The history of physics is full of moments when the constraints from observation outpaced the solutions from theory, when the data was ahead of the models and theorists had to do hard work to catch up. The development of quantum mechanics was driven by experimental anomalies, the photoelectric effect, atomic spectra, the stability of atoms, that the classical theory could not explain, and for which a new framework had to be invented from the ground up. General relativity was confirmed by observations, the precession of Mercury's perihelion, the deflection of starlight, the gravitational redshift, that required a complete reconceptualization of space and time to explain. In each case, the anomalies were not immediately resolved. They accumulated, they sharpened, and eventually they forced a conceptual breakthrough. The anomalies currently accumulating around dark energy, early galaxy formation, and the Hubble tension may or may not require a breakthrough of comparable magnitude. They may turn out to be resolvable within the existing LCDM framework, with careful modifications, a better treatment of stellar feedback, a better understanding of dust in early galaxies, a more accurate calibration of the distance ladder. They may require an extension of LCDM, a new dark energy model, a new dark matter physics, a modification of gravity at cosmological scales. Or they may, in the worst case for the model and the best case for the science, require something genuinely new, a new understanding of the vacuum, a new particle physics, a connection between dark energy and dark matter that we have not considered. The JWST team and the broader cosmological community are not, in general, making dramatic claims about which of these possibilities is correct. The prevailing attitude is one of watchful caution, taking the anomalies seriously, building better models, collecting more data, holding the uncertainty until the data resolves it. This is exactly the right scientific response. It is also, I will confess, slightly maddening when you are sitting outside the field and trying to understand what is happening, because the scientific caution makes it difficult to convey the urgency and importance of what is being observed. So let me attempt to convey it directly. If dark energy is evolving, if it is not constant, not lambda, but something more complex and dynamic, then the standard cosmological model that has described the universe for 25 years is wrong in a fundamental way. Not wrong in every particular, not wrong about the age of the universe, or the structure of the CMB, or the abundance of primordial elements, or the existence of dark matter, but wrong about the nature and behaviour of the dominant energy component of the universe, the component that constitutes 68.3% of its total energy budget, the component that is currently determining the rate at which the universe expands, and the degree to which structure will continue to grow in the cosmic future. If dark energy is not constant, then the universe's future is not what we calculated. The expansion history of the universe from now until its eventual end, whether that end is a big freeze in which the universe expands forever and all structure slowly dissipates into thermal equilibrium, or a big crunch in which a future negative dark energy drives the universe back toward a collapse, or some other scenario that the standard model does not currently include, is a question whose answer changes depending on what dark energy actually is. We do not know what dark energy actually is. We have known this, in a formal sense, since 1998. But for 25 years, the not knowing was comfortable because the simplest assumption that dark energy is a constant fit all the data well enough that the not knowing did not urgently demand resolution. The DESI data, the JWST Bright Galaxy Excess, and the Hubble tension have collectively made the not knowing urgent in a way it was not before. There is a question running beneath all of this that is more fundamental than any of the specific anomalies. It is the question of whether our entire framework for understanding the universe, the combination of general relativity, particle physics, and cosmological perturbation theory that underpins low CDM, is sufficient to describe the universe at the scales and epochs that JWST is now accessing, or whether, like Newtonian mechanics at the end of the 19th century, it is a highly successful approximation that will eventually need to be replaced by something deeper. Newtonian mechanics was not wrong in the sense of being useless. It put humans on the moon. It described planetary orbits with extraordinary accuracy. It governed the engineering of every machine built before 1900. It was wrong only at high velocities and strong gravitational fields, as special and general relativity respectively replace it. Lee CDM may be similarly limited, accurate over the range of observations for which it was calibrated, but requiring a deeper framework at the earliest epochs and highest energies that JWST is now exploring. This is not a comfortable thought for a community that has spent decades building Lee CDM into the most precisely constrained cosmological model in history. But it is the thought that the data is beginning to force, and it is a thought that connects directly to the third major anomaly in JWST's results. The one that arrives not from the cosmological scale but from the planetary scale, from a world 124 light-years away, where the question is not the fate of the universe, but the presence of life, because the K218b biosignature debate is, at its core, about the same problem that the impossible galaxies problem and the Hubble tension are about. It is about the limits of inference from observation. It is about what we can conclude and what we cannot when the signal we are measuring is at the edge of our instrument's capabilities. and the interpretation requires assumptions that may not be valid. In the K218b case, those assumptions are about atmospheric chemistry. In the cosmological case, they are about the physics of dark energy and structure formation. But the epistemological challenge is the same. We are at the frontier, where the data is real but its meaning is genuinely ambiguous, and where the temptation to leap to the most exciting interpretation must be balanced against the discipline of sitting with uncertainty until more evidence arrives. This balance between the excitement of discovery and the rigour of verification is what science, at its best, is made of, and it is what JWST, in its 3 years of operation, has required of the entire astronomical community in a more demanding and more public way than any previous instrument in the history of the field.